In the previous two videos, we saw how to solve a second order equation of the form a d2y dx squared plus b dy by dx plus cy equals 0. We now move to the problem of solving a second order differential equation where the right hand side isn't 0 but is a general function of x. So, as our first example, what we're going to be working towards is finding a solution of the differential equation d2y dx squared plus 3 dy by dx plus 2y equals 4x squared plus 2x plus 3. And this first example is going to end up giving us a method for solving such equations. So let's start working through this first example then. So to begin with, we've simply got to solve the equation d2w dx squared plus 3dw by dx plus 2w equals 0, which is precisely the sort of equation that we've been solving in the previous two videos. So the auxiliary equation is m squared plus 3m plus 2 equals 0, which has roots of m equals minus 1 or minus 2. So we can say that the solution of this equation is w equals ae to the minus x plus be to the minus 2x. We've now got to find values alpha, beta and gamma such that y equals ax squared plus alpha x squared plus beta x plus gamma is a solution of d2y dx squared plus 3dy by dx plus 2y equals 4x squared plus 2x plus 3. So we start with y equals alpha x squared plus beta x plus gamma, in which case dy by dx is 2 alpha x plus beta, and d2y dx squared is just 2 alpha. So d2y dx squared plus 3 dy by dx plus 2y is going to equal 2 alpha plus 3 lots of 2 alpha x plus beta plus 2 lots of alpha x squared plus beta x plus gamma. And if we collect together the different powers of x that we've got there, we've got 2 alpha x squared, which just comes from the final bracket in the line above. We've then got 6 alpha x plus 2 beta x. In other words, we've got 6 alpha plus 2 beta x coming from the two brackets in the line above. And then for the constant term, we've got 2 alpha plus 3 beta plus 2 gamma. And what we want is we want this expression here to be the same as the right hand side of our differential equation. So we want this expression here to be equal to 4x squared plus 2x plus 3. Looking at the x squared terms first of all, we're going to have 4 has got to equal 2 alpha. In other words, alpha has got to equal 2. We then also want 6 alpha plus 2 beta to equal 2, looking at the x terms. So 6 alpha plus 2 beta equals 2. I already know that alpha is 2, so that's 12 plus 2 beta has got to equal 2, which gives me beta equals minus 5. And finally, looking at the constant term, we want 2 alpha plus 3 beta plus 2 gamma to be equal to 3. 2 alpha is equal to 4, 3 beta is minus 15, so I've got 4 minus 15 plus 2 gamma has got to equal 3, so that is 2 gamma equals 14, so gamma must equal 7. In other words, we have found out that y equals 2x squared minus 5x plus 7 is a solution of the differential equation we're considering. So for part C, we've got to show that for these values of alpha, beta and gamma, in other words alpha equals 2, beta equals -5 and gamma equals 7, then big Y, which is equal to 2x squared minus 5x plus 7, plus W, which is ae to the minus x plus be to the minus 2x, is also a solution of the equation that we're trying to solve. Well, just got to do what we've been asked to do. So there's y. Differentiate y. We're going to get dy by dx is 4x minus 5 minus ae to the minus x minus 2b to the minus 2x. And d2y dx squared is going to be 4 plus ae to the minus x plus 4b to the minus 2x. So d2y dx squared plus 3 dy by dx plus 2y is going to be equal to 4 plus ae to the minus x plus 4be to the minus 2x. That's the d2y dx squared term. Plus 3 lots of 4x minus 5 minus ae to the minus x minus 2be to the minus 2x, which is the dy by dx expression, plus 2 times y, which is 2x squared minus 5x plus 7 plus ae to the minus x plus be to the minus 2x. And if we look carefully at that and simplify it, you'll find out that all of the terms cancel out, just leaving 4x squared plus 2x plus 3. So we've done what we've been asked to do. We've shown that this capital Y is also a solution of the equation d2y dx squared plus 3 dy by dx plus 2y equals 4x plus 2x plus 3. So capital Y is a solution of the equation as we required. Now, for the next, what this is doing is it's suggesting that y equals 2x squared minus 5x plus 7 plus ae to the minus x plus be to the minus 2x is actually the general solution of the differential equation. So notice that what we've got is that this general solution consists of two parts. The 2x squared minus 5x plus 7 is the special solution that we found in part B, and the ae to the minus x plus be to the minus 2x was the general solution of the differential equation, where the right hand side had just been replaced by 0. So let's carry on and try and finish this example off. We've got to find the particular solution of the equation for which y equals 4 and dy by dx equals 2 when x equals 0. So we've got y equals 2x squared minus 5x plus 7 plus ae to the minus x plus be to the minus 2x is our general solution. Putting x equals 0, y equals 4 tells me that 4 must be equal to 7 plus a plus b. In other words, a plus b must be minus 3. We can differentiate y. So we've got dy by dx is 4x minus 5 plus minus ae to the minus x minus 2be to the minus 2x. When x equals 0, dy by dx has got to equal 2. So we've got 2 equals minus 5 minus a minus 2b. So that gives me a plus 2b is minus 7. I've got a pair of simultaneous equations there that solve to give me a equals 1 and b equals minus 4. So I now know that the solution of the equation that meets the boundary conditions y equals 4 and dy by dx is 2 when x equals 0 is y equals 2x squared minus 5x plus 7 plus 1e to the minus x plus minus 4e to the minus 2x. So what this example suggests is that if we can find the general solution of the equation d2w dx squared plus b times dw by dx plus c times w equals 0, and we can find a solution of the differential equation a times d2y dx squared plus b dy by dx plus cy equals f of x, then the general solution of that differential equation will simply be of the form y1 plus w. Now we'll try and see why that's the case now. Suppose that we know that y1 is a solution of the equation a times d2y dx squared plus b dy by dx plus cy equals f of x, and y2 is any other solution of this equation. Then that means that we know that a times d2y dx squared plus b times dy by dx plus c times y1 must equal f of x, and exactly the same equation holds if we replace y1 by y2. If we subtract the two equations, then we've got a times the second derivative of y2 minus y1 plus b times the first derivative of y2 minus y1 plus c times y2 minus y1 must equal 0. So if we let w equal y2 minus y1, then we've got a times d2w dx squared plus b times dw by dx plus c times w must equal 0. So w is y2 minus y1. Rewrite that. We can say that y2 must be equal to y1 plus w. So any solution y2 is simply y1 plus a solution of the equation a d2w dx squared plus b times dw by dx plus cw equals 0. So we've now proved that if we can find the general solution of the differential equation with the equals 0 on the right hand side, and we can find a particular solution of the equation with the f of x on the right hand side, then the general solution of the equation a d2y dx squared plus b dy by dx plus c times y equals f of x will be of the form the particular solution y1 plus the general solution of the equation a d2w dx squared plus b dw by dx plus cw equals 0. We're going to call y1 the particular solution or the particular integral of the differential equation. And w is called the complementary function or the complementary solution of the equation. So the general solution is simply the addition of a particular solution and the complementary solution. So to find the general solution of the equation a d2y dx squared plus b dy by dx plus cy equals f of x, we're going to do for two things. First of all, we're going to find the general solution of the equation a d2w dx squared plus b dw by dx plus cw equals 0. That's the complementary solution of the original equation. Then, by intelligent guesswork, we're going to find a particular solution of the original equation. And then the general solution is simply the addition of the particular solution and the complementary solution. So let's have a go at doing this with some examples now. So we want to find the general solution of the equation d2y dx squared plus 4dy by dx plus 4y equals 4x plus 2. So we start off by trying to find a complementary solution. Now the complementary solution is the solution of exactly the same equation, except we have a naught on the right hand side. So we may as well just try and solve d2y dx squared plus 4dy by dx plus 4y equals 0. The auxiliary equation is m squared plus 4m plus 4 equals 0. That has a repeated root of m equals minus 2, which means that we know the solution of that equation is going to be y equals ax plus b times e to the minus 2x. So we've found the complementary solution. The right-hand side is a simple linear function, so it might well be a good idea to try y equals alpha x plus beta to see whether there's a linear function which is a solution of the whole differential equation. Now if we've got y equals alpha x plus b, then dy by dx is alpha, d2y dx squared is 0. So d2y dx squared plus 4dy by dx plus 4y is going to be 0 plus 4 alpha plus 4 alpha x plus beta. In other words, that is 4 alpha x plus 4 alpha plus 4 beta. And we want that to equal 4x plus 2. Well, if we look at the x parts of these expressions, we need 4 alpha to equal 4, which means that we need alpha equals 1. And then if we look at the constant part of these expressions, we've got 4 alpha plus 4 beta, we want to equal 2. In other words, we've got 4 plus 4 beta equals 2, because we know that alpha equals 1. So that means 4 beta's got to be minus 2, so beta's got to be minus a half. So we've got a particular solution of y equals x minus a half. Once we have got our particular solution and our complementary solution, then the general solution is simply the particular solution plus the complementary solution. So the general solution is y equals x minus a half plus ax plus b times e to the minus x. For our next example, we're going to find the general solution of the equation d2y dx squared plus 5dy by dx plus 6y equals 8 cos 2x plus 12 sine 2x. Again, we're going to start off by finding the complementary solution. So we're going to try and solve the equation d2y dx squared plus 5dy by dx plus 6y equals 0. The auxiliary equation is m squared plus 5m plus 6 equals 0. And solving that gives me m equals minus 2 or m equals minus 3. So the complementary solution is y equals a e to the minus 2x plus b e to the minus 3x. We now need to look for a particular solution. Now in this case, the right-hand side of our differential equation takes the form 8 cos 2x plus 12 sine 2x. So it seems sensible to start off trying to find a particular solution of the form y equals alpha cos 2x plus beta sine 2x. If we have y equals alpha cos 2x plus beta sine 2x, then dy by dx is minus 2 alpha sine 2x plus 2 beta cos 2x. And d2y dx squared is going to be minus 4 alpha cos 2x minus 4 beta sine 2x. So, d2y dx squared plus 5 dy by dx plus 6y is going to be minus 4 alpha cos 2 alpha, sorry, minus 4 alpha cos 2x minus 4 beta sine 2x, that's d2y dx squared, plus 5 lots of minus 2 alpha sine 2x plus 2 beta cos 2x, so that's 5 lots of dy by dx, plus 6 lots of alpha cos 2x plus beta sine 2x, which is just y. Tidying that up, so collecting together the sine terms and the cos terms separately, we get 2 alpha plus 10 beta cos 2x plus 2 beta minus 10 alpha sine 2x. We want that to equal 8 cos 2x plus 12 sine 2x. So we need 2 alpha plus 10 beta to equal 10. Sorry, 2 alpha plus 10 beta to equal 8. And minus 10 alpha plus 2 beta to equal 12. And that gives me alpha equals minus 1 and beta equals plus 1. So we have a particular solution of y equals minus cos 2x plus sine 2x. The general solution is simply the particular solution plus the complementary solution. So the general solution is y equals minus cos 2x plus sine 2x plus a e to the minus 2x plus b e to the minus 3x. Okay, our next example, then we're going to try and solve the equation d2z dt squared plus 5dz by dt plus 6z equals 20e to the 3t. But this time we've got some boundary conditions. We've got when t equals 0, z has got to equal 2, and dz by dt has got to be minus 3. So, same process as before. Find the complementary solution first of all. So we've got to solve the equation d2z dt squared plus 5dz by dt plus 6z equals 0. The auxiliary equation is m squared plus 5m plus 6 equals 0, which has roots m equals minus 2 or m equals minus 3. So the complementary solution is z equals a e to the minus 2t plus b e to the minus 3t. In this case, the right-hand side of our original differential equation is 20e to the 3t, so it might well be sensible to start trying to find a particular solution of z equals alpha e to the 3t. If z is alpha e to the 3t, then dz by dt is going to be 3 alpha e to the 3t, d2z dt squared is going to be 9 alpha e to the 3t. So d2z dt squared plus 5dz by dt plus 6z is going to equal 9 alpha e to the 3t plus 5 times 3 alpha e to the 3t, which is 15 alpha e to the 3t, plus 6 lots of alpha e to the 3t. Now that clearly simplifies to 30 alpha e to the 3t, which will equal 20 alpha e to the 3t if alpha is 2/3. So we have as our particular solution is z equals 2/3 e to the 3t. The general solution of the equation now is z equals 2/3 e to the 3t plus a e to the minus 2t plus b e to the minus 3t. But we want the solution that satisfies that when t equals 0, z is 2, and dz by dt is minus 3. So, when t equals 0, z has got to equal 2, so we've got 2 must equal 2/3 plus a plus b, so a plus b must be 4/3. dz by dt is 2e to the 3t minus 2a e to the minus 2t minus 3b e to the minus 3t. When t equals 0, we want dz by dt to be minus 3. So I've got minus 3 must equal 2, take away 2a, take away 3b, which tells me that 2a plus 3b has got to equal 5. Solving the simultaneous equations gives me a equals minus 1 and b equals 7/3. So I've got my particular solution. The required solution is z is 2/3 e to the 3t minus e to the minus 2t plus 7/3 e to the minus 3t. Now let's have a look at a very, very similar example. It's exactly the same as the previous example, except the right-hand side now is 4e to the minus 3t. So finding the complementary function is exactly what we did before. So we've got the complementary solution is z equals ae to the minus 2t plus be to the minus 3t. Now it would be very tempting on this one to try z equals alpha e to the minus 3t. In which case, dz by dt would be minus 3 alpha e to the minus 3t, d2z dt squared would be 9e to the minus 3t. And if we work out then d2z dt squared plus 5 dz by dt plus 6z, we get 9 alpha e to the minus 3t minus 15 alpha e to the minus 3t plus 6 alpha e to the minus 3t. That unfortunately becomes naught. So it would be very, very difficult to make that equal to 4e to the minus 3t. So the important thing is to try and work out what's gone wrong on this particular case. And it doesn't work because e to the minus 3t is part of the complementary function. So we know that e to the minus 3t, if I have z equals e to the minus 3t, or z equals be to the minus 3t, or z equals alpha e to the minus 3t, then d2z dt squared plus 5 dz by dt plus 6z equals 0. So there's no chance that putting z equals alpha e to the minus 3t is going to work in this case. We need to be a little bit more subtle. And the subtlety here is that we need a little trick. Instead of trying z equals alpha e to the minus 3t, we're going to try z equals alpha t e to the minus 3t for the particular solution. So, here we go. Try z equals alpha t e to the minus 3t. Product rule gives me dz by dt is alpha e to the minus 3t minus 3 alpha t e to the minus 3t. Product rule again gives me d2z dt squared is going to be minus 3 alpha e to the minus 3t. That's the derivative of the first term in the line above. Then I've got to differentiate the minus 3 alpha t e to the minus 3t, and that's going to give me minus 3 alpha e to the minus 3t plus 9 alpha t e to the minus 3t. And this simplifies to minus 6 alpha e to the minus 3t plus 9 alpha t e to the minus 3t. So d2z dt squared plus 5dz by dt plus 6z is going to be minus 6 alpha e to the minus 3t plus 9 alpha t e to the minus 3t. That's my d2z dt squared. Plus 5dz by dt, which is 5 alpha e to the minus 3t minus 15 alpha t e to the minus 3t. Plus 6z, which is plus 6 alpha t e to the minus 3t. And that simplifies down to simply minus alpha e to the minus 3t, which will be equal to 4e to the minus 3t, provided alpha is equal to minus 4. So I have now a particular solution of z equals minus 4t e to the minus 3t. The general solution is the particular solution plus the complementary solution. So the general solution is z equals minus 4t e to the minus 3t plus a e to the minus 2t plus b e to the minus 3t. We're now going to try and find the solution of the equation d2y dx squared plus 4y equals 6 cos x plus 9 sin x, with the boundary conditions that when x equals pi by 2, y is equal to 4, and dy by dx is equal to 1. Start off with the complementary solution as usual. So we've got to solve the equation d2y dx squared plus 4y equals 0. The auxiliary equation is m squared plus 4 equals 0. In other words, m is 0 plus 2i or 0 minus 2i. So the complementary solution is y equals e to the nothing times x times by p cos 2x plus q sin 2x. In other words, we've got a complementary solution of p cos 2x plus q sin 2x, because e to the nothing is just 1. For the particular solution, it would seem sensible to try y equals alpha cos x plus beta sin x, in which case dy by dx is minus alpha sin x plus beta cos x, d2y dx squared is minus alpha cos x minus beta sin x. So d2y dx squared plus 4y is minus alpha cos x minus beta sin x plus 4 lots of alpha cos x plus beta sin x, which simplifies to 3 alpha cos x plus 3 beta sin x. Now we want this to equal 6 cos x plus 9 sin x, so I need alpha must equal 2 and beta must equal 3. So I've got a particular solution of y equals 2 cos x plus 3 sin x. And finally, I've got a general solution of y equals 2 cos x plus 3 sin x plus p cos 2x plus q sin 2x. But I need the solution which satisfies that when x equals pi by 2, y is equal to 4, and dy by dx is equal to 1. So putting x equals pi by 2 in, I've got y must equal 4. So that gives me 4 equals 2 cos pi by 2, which is nothing, plus 3 sin pi by 2, which is just 3, plus p times by cos pi, and cos pi is minus 1, plus q times sin pi, and sine of pi is 0. So in other words, I've got 4 equals 3 minus p, which means that p must be minus 1. Now we know that dy by dx is going to be minus 2 sine x plus 3 cos x minus 2p sine 2x plus 2q cos 2x. When x is pi by 2, we want dy by dx equals 1. So we've got 1 must equal minus 2 sine pi by 2, which is just minus 2, plus 3 cos pi by 2, which is 0, minus 2p sine pi, which is 0, plus 2q times by cos of pi, which is minus 1. In other words, we've got 1 equals minus 2, take away 2q. So we've got 3 must be minus 2q, so q is minus 3 over 2. So the required solution in this case is y equals 2 cos x plus 3 sin x minus cos 2x minus 3 over 2 sin 2x. And for example 7 then, we've got to find the general solution of the equation d2y dx squared plus 4y equals 12 cos 2x minus 4 sin 2x. The complementary solution of this is exactly the same working as the previous example. So we've got d2y dx squared plus 4y equals 0, m squared plus 4 equals 0 is the auxiliary equation. That gives me m equals 2i or minus 2i, which means that we have got the complementary solution is y equals p cos 2x plus q sin 2x. Now, cos 2x and sin 2x are both possible parts of the complementary solution. So there's no point us trying a particular solution of the form alpha cos 2x plus beta sin 2x. It will just collapse completely. So we've got to imitate the trick that we used 2 examples ago and say let's instead try y equals alpha x cos 2x plus beta x sin 2x. If we try that, then dy by dx using the product rule is alpha cos 2x minus 2 alpha x sin 2x plus beta sin 2x plus 2 beta x cos 2x. Using the product rule again, we can find d2y dx squared, which is a fairly monstrous little expression, minus 2 alpha sin 2x minus 2 alpha sin 2x minus 4 alpha x cos 2x plus 2 beta cos 2x plus 2 beta cos 2x minus 4 beta x sin 2x. And now if we collect together the cos 2x and the sin 2x terms, we get 4 beta minus 4 alpha x times by cos 2x plus minus 4 alpha minus 4 beta x times by sin 2x. So d2y dx squared plus 4y is equal to 4 beta minus 4 alpha x times cos 2x plus minus 4 alpha minus 4 beta x times by sin 2x plus 4 lots of alpha x cos 2x plus beta x sin 2x. And that just leaves me with all the alpha x cos 2x terms cancel, the beta x sin 2x terms cancel, so we're just left with 4 beta cos 2x minus 4 alpha sin 2x, which will equal 12 cos 2x minus 4 sin 2x if beta is equal to 3 and alpha equals 1. So that means that I've got a particular solution is x cos 2x plus 3x sin 2x. So the general solution of this differential equation is y equals x cos 2x plus 3x sine 2x plus p cos 2x plus q sine 2x. That's a pretty nasty example, but it is fortunately the final example in this video. You may find this table useful when you're trying to make decisions about what to use as your particular solution. So if f of x is a constant, just try y equals a constant. If f of x is a linear function, just try y equals alpha x plus b, in other words, another linear function. If f of x is a quadratic, try y as a quadratic. If f of x is lambda e to the kx, then try alpha e to the kx if e to the kx is not a complementary solution. If it is, try alpha x e to the kx if e to the kx is a possible complementary solution. And then the final one here, we've got p sine kx plus q cos kx. Well, we'll try alpha sine kx plus beta cos kx, provided cos kx and sine kx are not possible complementary solutions. If cos kx and sine kx are possible complementary functions, then you're going to have to try the more complicated alpha x sine kx plus beta x cos kx. So that concludes our look at solving second order differential equations of the form a d2y dx squared plus b dy by dx plus cy equals f of x.